Welcome back. In this presentation, we will be discussing the pressure forces on submerged surfaces. Consider a thin plate, curved plate, shown in red, submerged in a liquid. On the upper surface, there would be a pressure. Let the pressure be P at a point. On a point directly below that point, on the lower surface, there will again be a pressure P prime. Both the pressure would be equal to rho GH, where H is the depth from the free surface of the liquid. The two pressures would be equal, and therefore, if we need to calculate the pressure force on the lower surface, that will be equal to the pressure force on the upper surface. On a thin plate, the force on the upper surface is the same, though in the opposite direction as that on the lower surface. Let us consider next the hydrostatic force on a vertical surface. We've seen earlier that within a liquid, the force varies linearly with the depth of the point. So the pressure on this plate, which was shown in red, is as shown. Clearly, if we consider the width of the plate as shown, there would be a pressure prism on that surface, which would look like this. The magnitude of the force on the upper surface would be rho g h1, where h1 is the depth of the upper surface from the free surface of water, and the pressure at the lowest end of this plate would be rho g h2. The total force would be acting at some point in between the two ends of the plate, and the total force would be found out by integrating over a small area dA. Let us consider an element of height dH at a depth h from this free surface. The pressure on that little element would be rho gh, and so the force on the element would be rho gh times bdh, where bdh is the area of that element. To find the total force on the plate, we have to integrate this over h. From h is equal to h1, the depth of the upper point of the plate, to h2, the depth of the lower point of the plate. And if we do a simple integration assuming rho, b and g constant, we get the total horizontal force as 1/2 rho g b h2 square minus h1 square. Let us consider another geometry, a circular plate. The pressure prism on the circular plate would look like this. This is the hydrostatic pressure variation, and the force would be integral of rho gh times dA over the whole area A, which is rho g times the integral of h dA. Integral h dA can be written as the depth of the centroid, rho g times depth of the centroid hc times the area of the plate A. Rho GHC is recognized as the pressure at the centroid of the plate, so that the total hydrostatic force on this vertical plate is seen as the pressure at the centroid times the area of the plate. F is pressure at the centroid times the area of the plate. This is the relation that we use most often in calculating pressure on the plate. Let us do an example. We have an equilateral triangular plate with each side equal to B. It is immersed in a liquid of density rho to a depth such that the vertex of the triangular plate is at depth h0. We have to find the location of the centroid. We know that the depth of the centroid from the tip of the plate is 1/3 of the height of the plate, and the height of the plate is √3b by 2, so that the centroid is at a depth of b by √3. The total depth of the centroid is h0 plus b by √3. And so the total force is the pressure at the centroid, which would be rho g into h0 plus b by √3 multiplied by the area of the plate. The area of the plate being b times √3b by 2 divided by 2. Now let's find out the forces on curved surfaces. Let us consider a two-dimensional plate curved as shown in this figure and immersed in a liquid of density rho. We measure h downwards from the free surface. The pressure distribution on the upper plate would be as shown. The pressure acting normal to the plate everywhere and increasing with depth. Let us consider the volume of the liquid above the plate. Let's isolate this as a free body. If Fy is the vertical force acting on the plate because of the liquid, then on this free body of liquid, there is a force due to plate equal to Fy acting upwards. The reaction to the force on the plate by the liquid. The only other vertical force on this free body is the weight of that liquid resting above the plate up to the free surface. So the vertical component of pressure force on the surface submerged in liquid is equal to the weight of the liquid that can be supported on the surface up to the free surface of the liquid. Let us next consider the horizontal force on this submerged surface. Same surface. Let the horizontal force because of liquid on the surface be Fh as shown. Let us consider this body of fluid and draw a free body diagram of this body of fluid. Let us draw the horizontal forces on this body of fluid. Then, on this free body diagram, there are two horizontal forces. One, the Fh, the reaction of the force on the plate acting to the left, and a horizontal force acting on the flat surface to the left of this body. This would be the hydrostatic force varying linearly from the top to the bottom. This is the force we have already calculated. This surface is flat, so by the relation that we derived for the horizontal force on a flat vertical surface, this force is equal to the pressure at the centroid of this place times the area of this vertical flat plate. To evaluate the force on this vertical flat plate, let the white area represent the projection of the original plate onto vertical plane. The pressure distribution on this is as shown. At depth h, let us consider an area dA. The pressure on this area dA is rho GH, and the force is rho GH times dA. We can find the total force by integrating this over dA, and so that we get the horizontal force as P H bar times AV, where P H bar is the pressure at the centroid of the projected area and AV is the vertically projected area. This is then the relation for the horizontal force. The pressure at the centroid of the projected area multiplied by the projected area of the surface. So, the two rules finding the horizontal and the vertical component of pressure forces are that the horizontal component of the pressure forces is equal to the pressure at the centroid of the vertically projected area times the projected area, and the vertical component of the pressure force is equal to the weight of the liquid that can be supported on the surface up to the free surface of the liquid. Let's do an example. Let's consider a cylindrical body which is immersed in a liquid as shown. On the left, the free surface of the liquid extend up to the topmost point of the cylinder, and on the right, the free surface of the liquid is only up to the diameter at the middle. If the radius of this cylinder is 1 meter, the depth of liquid on the left is 2 meters and on the right is 1 meter. To determine the forces on this, let us consider force on each of the 4 quadrant of the circular cylindrical surface. On quadrant 1, there are no forces. Let us first look at the vertical force. On the quadrant 2, the vertical force is equal to the weight of the water up to the free surface which is supported on that surface, which is shown as the blue area on this picture. On quadrant 3, the weight of the liquid that would be supported on quadrant 3 would be as shown. This would be a weight which is downward, but from the very first slide in this lecture, we have shown the force that would be on the upper surface would be same as force in the bottom surface. So, the vertical force which is upward on this surface in quadrant 3 would be equal to the weight of this area of the liquid shown. On the fourth quadrant, the force would be the weight of the blue, the darker blue area of the liquid shown. So, per unit depth, we can evaluate these areas and find out the total force. On quadrant 2, the force is downward, while on quadrant 3 and quadrant 4, the force is upward. On the quadrant 1, the force is 4.21 kilonewton downwards, and on second and third quadrants, on third and fourth quadrant, they are 34.99 kilonewton upwards and 15.26 kilonewton upward. We can sum up the three and find out the total vertical force on this circular cylinder per unit depth into the paper. Let us next find the horizontal force. Again, there will be no force in the first quadrant. On the second quadrant, it would be a triangular pressure variation over 1 meter depth. The net force would be the pressure at the centroid of the projected area times the vertically projected area. The vertically projected area, of course, a rectangle of depth 1 meter. So, the depth of the centroid would be 1/2 meter. On quadrant 3, the gray pressure prism is the force on quadrant 3. This again is found out by the same formula. The projected area here is again a rectangular plate of height 1 meter. The centroid of that plate would be 0.5 meter from the top of this plate, and so the depth of the centroid from this free surface is 1.5 meter. So pressure here would be rho times g times 1.5 meters, and the force is obtained by multiplying it by the area of this projected area. On the fourth quadrant, the pressure variations is as shown. The depth of the centroid would again be at 1/2 meter from the top of this, and therefore all the three horizontal forces have been determined. They are respectively rho gh, where h is the depth of the centroid for each of the element, into area of the plate. If the depth of the cylinder normal to the paper is considered 2 meters, then these are the forces. The first two are to right and the last one is to left. We can add up to find out the total force on this circular cylinder gate of 2 meters depth normal to the screen. Let us consider the next example as the force on a dome of an oil tanker. It is a cylindrical oil tanker with a hemispherical dome on it. It contains oil, and the pressure of this is measured by a mercury manometer rising to a height of 20 centimeters. So first we will find out the pressure at the bottom of the tank. The gauge pressure at the bottom of the tank is rho of mercury times g times the height of mercury, which is 20 centimeters. So this pressure is 26.7 kilopascals. This pressure of 26.7 kilopascal would mean that the pressure in the oil on the dome, inside the dome, is higher than the atmospheric pressure. Let's find out what is the height of oil that will result in this pressure of 26.7 kilopascal gauge at the bottom of the tank. Rho G H should be equal to 26.7 kilopascal. Rho of oil is 0.8 into 10 to the power 3 kilogram per meter cube. G is 9.8. And this multiplied by H would give you the pressure 26.7. The result is 3.40 meters from the bottom. So a pressure of 26.7 kilopascal at the bottom of the tank would be obtained if the oil extends up to a height of 3.40 meters in an opened tank. So the pressure variations in this vessel is equal to the pressure variations in an open tank in which the oil is standing up to a height of 3.40 meters. That is, the pressure variations within the tank are as if the free surface oil is up to 3.4 meters from the bottom. Clearly then, the vertical force on the hemispherical cap is equal to the weight of oil over and above the dam, shown as gray in this picture. We can easily evaluate that volume as here. Volume is pi into 0.4 meter square, which is the area of cross section, into 3.4 meters minus 1 meter, that is 2.4 meters. This would be that volume of this cylindrical vessel. From this, I have subtracted the volume of the hemisphere where there is no oil, and so the total volume of this gray portion is 0.87 meter cube. And so the vertical force is the weight of this oil, which is the density of the oil times G times this volume, 6.83 kilonewtons upwards. Of course, there will be no horizontal force because of the symmetry of the hemisphere. Let's do another example. An aquarium has a quarter cylindrical glass plate for viewing the fishes. The glass plate is as shown in red in this figure. What are the forces on this glass plate? Because of the water. These forces would be because of this pressure distribution, which at the top of this quarter cylindrical glass plate is because of 1 meter depth of water, at the bottom because of 2 meter depth of water. Integration of this pressure force would be quite complicated, but this is simplified by using the two rules that we obtained above. To determine the vertical force on the bottom of the glass plate, we recognize that this would be equal to the downward vertical force on the top of the glass plate if there was water up to the height of the free surface. So it is weight of this blue water prism shown. This weight is easy to find because volume of that water is equal to the volume of that square prism of water plus a quarter cylinder prism of water. And the horizontal force would be equal to the horizontal force on the vertically projected area of this window. Vertical projected area, of course, would be a rectangle of height 1 meter. And so it would be the pressure at the centroid of this plate, this projected area, which would be 1.5 meter from the free surface. And so this pressure would be rho times G times 1.5 meters, and we multiply by the vertically projected area to find the vertical component of the pressure forces. This is the horizontal force, and the vertical force is rho G times the volume of the water that could stand on the surface. Let us now do one more example where the force needed to open a door of an underwater car. Suppose a driver with a car takes a plunge in water and the car comes to rest at the floor of the pond 8 meters below the water lines. The dimension of the car are given. If the driver wants to open the door of the car, shown in broken lines here, what force would he need to apply? Measuring distance vertically downwards from the water line, the force would be the pressure at the centroid again times the area, vertical area of the door. The centroid of the door is at the middle of the rectangular door, so it is at a depth of 6.4 meters plus 1.4 meter by 2 or 7.1 meter. So the force would be 10 to the power 3 kilogram per meter cube. The density into 9.81 Newton per kilogram, the value G into 7.1 meter, the depth of the centroid, multiply by the area of the door, which is 1.4 meter into 1 meter, or is 97.5 kilonewton. The moment he would need to apply would be this force into 0.5 meters if he applies a force at the middle of the door. 48.75 kilonewton meter. This is far beyond the capability of a human being. So, if this is a situation that exists, the driver cannot get out, cannot open the door. So, is she doomed? No. She could lower the window if that is possible. If the electrical system is not broken down, she could lower the window, and as water enters the cabin, the forces on the back of the door would balance the forces from outside, keeping the door closed. And so it is possible that before the water inside reaches the top of the cabin, the force may reduce from 97.5 kilonewton to a figure which can be handled by the driver. Let us next consider the center of pressure on a submerged surface. For this, we will deal only with plane surfaces, flat surfaces. Let's consider an inclined surface at an angle theta as shown. The gray area shows the plane form of that surface. There's a pressure forces acting on the surface. The pressure variation, of course, would be linear rho GH, where H is the vertical depth from the free surface. If we measure S, the distance from the free surface along the slope of the plate, at any location S, the depth from the free surface is S sine theta. And the force on a strip of width ds on the surface would be rho gs sine theta into area dA of that strip. So this can be written as, we can take rho g sine theta outside the integral, and so this force is rho g sine theta integral S dA. Integral S dA over the whole area is nothing but the distance S of the centroid, the CG, times the area. So that the force is pressure at the centroid times the plate area. The same result as we obtained above. This is the force. But where is the center of pressure? Center of pressure is obtained by keeping this total force at a location such that the moment of this total force at that location is equal to the moment of the distributed force. The moment of the distributed force is obtained like this. The moment of the force on this element dA at distance S about origin O is minus S times the force rho g S sine theta dA. This is negative because this moment is clockwise. Now, to find the total moment, we integrate over the area. The S square dA, this term, integral over A is nothing but this, the second moment of area about the axis perpendicular to the screen passing through O. So that the moment now is rho g sine theta times the second moment of area IYY O. Now this moment should be equal to the distance S of the center of pressure, SCP, multiplied by the total force which was determined in the last slide as the pressure at the centroid, rho g SCG times the area, A psi, area A. So that the SCP is obtained as IYYO divided by SCGA. This is the distance of the center of pressure measured along S from the free surface. But this is in terms of IYY about O, which is not easy to find. It will vary with whole lot of things like an angle theta. So let us find out IYYO in terms of IYY about the centroid of the plate. And for this we use the parallel axis theorem. The parallel axis theorem says the second moment of area about any arbitrary point O is equal to the distance of that point O from the centroid squared, SCG squared times the area of the plate plus the second moment area about the centroid. Second moment area about the centroid is the property of the area. Using this in the first relation, we get SCP, the location of this center of pressure, as the location of the CG, SCG, plus IYY about CG divided by SCGA. So clearly the center of pressure is always below the center of gravity. But this distance between centroid and the center of gravity decreases as SCG decreases. For a depth of about 2 meters, so depth of the center of pressure is almost at the same location as depth of the centroid if the top edge of the surface is more than 2 meters from the free surface of water. Let us determine what is the force of buoyancy from whatever we have done so far. Let's consider a body immersed within a liquid. The free surface is marked. Let's split the body in two halves about its meridian. The vertical force acting on the bottom half, which will act upward at the bottom, is equal to the weight of the water support or weight of the liquid supported by this. So weight of the darker blue column of water up to the lower half surface. This is of course acting downwards on the top, and so it is acting upwards on the surface shown. Now the other half of the surface supports this column of water above it. So the pressure force on this upper half of the body is downwards equal to the weight of this column of water. The difference of the two obviously is the weight of this volume of water, and this would be upwards. So the buoyancy force is equal to the weight of water equal to the volume of the body, or weight of the water displaced by the body. This is what you studied as Archimedes' principle in your high school. The buoyancy force is equal to the weight of the liquid displaced, rho times g times the volume of the body itself, and it is upward. This is, of course, independent of the depth to which the body is suspended. If the density of the fluid does not change with depth. Let's do a very simple example. A 400 kilogram buoy with a 0.8 meter radius is tethered to the bed of a lake. What is the tensile force on the cable? For this, of course, we'll draw a free body diagram of the buoy. And on this free body diagram, we would have the buoyancy force and the tension in the string. So the tension on this and the weight of the buoy itself. So the buoyancy must be balancing the weight of the buoy plus the tension. And so tension would be equal to the buoyancy minus the weight of the buoy. To find the buoyancy, we find out the volume of the displaced water, which is spherical of 0.8 meter radius, which is 2.145 meter cube. And so the buoyancy is rho g times the volume, 21 into 10 to the power 3 Newton. This is the free body, 21 into 10 to the power 3 Newton, and upwards, and the weight 400 kilogram, which is 3.9 into 10 to the power 3 Newton, downwards, and the difference must be balanced by tension, which would give you 17.1 into 10 to the power 3 Newton. Let us next consider the stability of floating bodies. Let us consider a fully immersed body and it's floating. So the buoyancy force must be equal to the weight of the force. First, let us consider a geometry or an orientation in which the heavy part of this rectangular body is downwards. So the center of gravity, C, would be below the center of the body, C as shown, and from this the weight W would be acting. The buoyancy force Fb can be considered to act center of buoyancy B, which is located at the center of the volume. In this case, it is the center of the rectangle. In equilibrium position, the two forces are equal and there is no moment on the body because the weight force and the buoyancy force act in the same line. But if this body is disturbed slightly so that it's tilting to the right, it is easy to see that the weight and the buoyancy force would now produce a couple, and this couple would have a restoring moment because this moment is counterclockwise, which will tend to upright the body. Consider the other case where the body is floating with the heavy and up. The center of gravity is now above the middle point, and if the body now tilts to the right as shown, the weight and the buoyancy form a clockwise couple which will further upset the equilibrium and the body would topple over. Let us consider this ship which is floating in equilibrium in an ocean. There is a weight that acts at the center of gravity, C, and the buoyant force which acts at the center of buoyancy, B. The center of buoyancy is at the centroid of the displaced water. So that is below the waterline, the volume of the water, volume of the ship below the waterline. If the ship tilts to the right, then the volume of the water towards the right is more and the volume of the water displaced is less towards the left, and so the center of buoyancy shifts to the right. Now we see that the buoyant force Fb acting at the center of buoyancy and the weight W acting at the centroid form a couple which is counterclockwise, which will tend to restore the ship back to vertical. This is a stable orientation of the ship. However, we can imagine a situation where if the center of gravity is too high, then the buoyancy center, even if it shifts to the right, but the center of gravity shifts to the right more, and the two forces, the buoyant force and the weight force, form a clockwise couple, which is a toppling moment, because it will topple the ship and the ship might turn turtle. To analyze this, let us consider this simple shape of the ship, where O is at the waterline, C is the centroid. Now, if the ship tilts, B is the original position of the center of buoyancy, B prime is the new position of the center of buoyancy, which is towards the right of B, because there is more water on the right, which is displaced, and less on the left. So there is added buoyancy on the right and lost buoyancy on the left. Because of this, the center of buoyancy shifts towards the right. Let's take a larger view of this. Let's assume the ship tilts through angle alpha. B prime is the new location of the center of buoyancy. B is the old center of buoyancy. Let's determine B, B prime. This is B, B prime. And let's denote it by L. The force Fb now acts at the new center of buoyancy. If the center of buoyancy is displaced to a distance L to point B prime, then taking the moment about B, we get Fb into L should be the net moment of the additional and lost buoyancies. Added because of the additional buoyancy and moment lost because of lost buoyancy. So, we consider area dA of a strip at the waterline of the ship at a distance y from the center line along the deck of the ship. The additional buoyancy dFB because of this is the density of waters times G times y sine alpha is this height. This distance is y, so this is y sine alpha. Y sine alpha dA is the volume of the gray area, the darker gray area. So this is the additional buoyancy. And the moment it creates is about the point O. This point O is multiply this buoyancy force by F. So dm is rho w g y square sine alpha dA. So the change in moment produced is you integrate this over the whole area of the water line. This additional moment is now found out to be rho w g sine alpha times Ixx, where Ixx is the second moment of the platform area at the water line about the axis of the tilt, that is perpendicular to the screen at point O. This additional moment must be equal to L times the force of buoyancy, which is equal to the weight of the ship. So this is L, which is the distance between B and B prime. The shift in B is rho wg sine alpha Ixx divided by W, the weight of the ship. If we draw a line vertically through B, it will intersect the center line of the ship, which passes through B and O at point M. This point M is termed the metacenter of the ship. So this point M, the metacenter of the ship, the distance BM plays a very important role. It is called the metacentric height. The distance between the center of buoyancy B of the ship in the normal orientation and this point M. Clearly, BM distance is L divided by sine alpha, and so it is rho wg Ixx divided by W. This ship would be stable if the center of gravity lies within the segment BM. The lower the center of gravity, the more stable is the ship. If the center of gravity lies above point M, then the ship is unstable. So, while loading a ship, the captain and crew of the ship ensure that the CG of the ship is low enough, well below the metacenter. The metacentric height MB prime is the property of the ship geometry and the weight of the ship. It plays a very important role in flying of the ships. Thank you very much.